Now for the first example there, you should feel okay with handling this function. There's not really a ton of, anything new or crazy from what we've already talked about. So I'm going to let you just go with it and see. You probably can sketch this whole curve, but anyways, if there is a spot where we get stuck, then I'll stop us there and we'll catch up together, okay? But give this one a try with these fractional cube root exponents. All right, so I'm going to try and catch up to you. It looks like most of you are already on your way. So this will be 10 over 3 x to the 2/3 minus 20 over 3 x to the 1/3. And one convenient way to factor this would be 1/3. Does anybody, how can we make sense of the exponent 1/3? What's one way you could think of it?
Cube root.
Yeah, so cube root. I think I already said that actually, so that's probably a bad question. But so we have two solutions here. First one, I'll take the easy one. What's the tougher one? Yeah, 8's correct. So you're trying to, usually we just solve it by looking at it, but you could actually go to the trouble of solving this. So 1/3 would be equal to 2, cube both sides, and you get x equals to 8. Cube both sides. Okay, so there's our critical points. Now let's,
Where'd 8 come from?
8 is what makes this piece equal to 0.
What piece? Your head is in the way.
Sorry, I'll move then.
Oh.
So let's take a look at the second derivative, which most of you have as well. We're going to do the same thing, a bit of factoring. So the second derivative is going to be, let's see here, 20 over 9 x to the negative 1/3. Take away 20 over 9 x to the negative 2/3. Now, when we factor this out, definitely can factor out 20 over 9. What else would you like to factor out of this?
X to the negative 1/3.
Yeah, we could take out an x to the negative 1/3. Sure, we can do it that way. So that means I'm going to have a 1 take away x to the negative 1/3. So where will these be equal to 0? I'll take the easy one. Sorry, I just lied. That's not where it equals to 0, but it's still an inflection point. How come? How come it doesn't... It even fooled me, so maybe I'll rewrite it in case you can't see why. If I was to rewrite this, it would be like this. So it's still in our list, but I'm just going to be careful and I'm not going to say it equals to 0. It still causes a problem, so x equals 0 would be one of those spots. The other spot?
1.
Yeah, 1. So when this equals to 1, there we go. So now I'm going to make my number lines, talk about those points, 0, 1, and 8. So here's my first derivative, and here's my second derivative. 0, 8, and the other one I wanted was 1. Let's see here, so say it's something like that. Okay, so now we most likely would want to use a calculator here. Since there are cube roots involved, I think that's probably a fair game. So why don't we figure out the pattern on the number lines? So the pattern I get from my calculator here is positive, negative, positive. And we'll do the same for second derivative. So I have, hopefully someone can verify this, in case I put it in my calculator wrong. Anybody else have negative, negative, positive? Alright, in honesty, did anyone else do it?
Working on it.
Working on it? Okay, fair enough. And let's see here. So I'm pretty sure I have this in my calculator properly. And I think that looks that's all right. Okay, so now I want to take my points, so at 0, 1, and 8. So let's figure out what those points would be. At 0, it would also be 0. At 1, 2 minus 5 is 3. Negative 3, sorry. And the last one is at 8. So let's see here. The cube root of 8 is 2. 2 to the 5 is 32. So 64. And then 16 is times 5. I can do it. 80. So 64 take away 80. Negative 16. Yeah. Okay, so there we go. Those are our points. 0, 0. 1 over 3 down. And 8, negative 16. So there's 8. And negative 16 will be right there. Okay, so at this point I'm going to assume you guys are getting a little bit more comfortable with walking along, so I'm going to do it a little quicker. The first part is increasing concave down, so it's going to go up like this. Then it's going to be decreasing concave down as it makes its way through. Then decreasing and concave down. Sorry, now I've lost my train of thought. Where was I? At 1. So sorry, decreasing concave up. That's where it went. Okay, so right now I'm in this section here, which is decreasing concave up. And then the final section, I'm increasing in concave up. So it's going to look something weird like this for the scale that I have. Okay. So we're going to try the last one then. I wanted to try 2 of these with you. I almost kind of feel like we need to give like a little group hug before we start this one. There's a challenge to this one. We definitely need a little bit of extra help. So just bear with me while we walk through it. I'll try to go a little slow. Just the algebra on this one is a little tougher. So anyways, I'm going to walk you through both derivatives, and hopefully it's not soul-crushingly bad. I don't think it's quite there, but anyway. Okay. So I'm probably going to rewrite this to do the derivative. So that means my derivative is going to be negative 1 plus e to the negative x. Then it'll be negative 2. And I've got this chain rule piece in here. So the derivative of the chain rule piece will be e to the negative x times negative 1. So to make it look a little prettier, that's going to be negative times a negative. So that'll disappear. It'll just be 1 over e to the x and 1 plus e to the negative x squared. So let me double check this because I have been known to make the odd mistake.
E to the x was in the bottom as well.
Well, I just took the negative exponent.
Oh yeah.
I just took that negative, moved it down. You don't have to, but I decided to. Now, so the question then becomes, is there any critical points here? Well, is there anywhere we could make that equal to 0? No, because there's a 1 on top. There's nothing but a constant of 1. Can we divide by 0 here? Can we make it undefined? Yeah, e to the x won't ever be negative. E to the negative x won't be negative either. So in this case, those ones there's no critical points that we're looking for here. What does that mean then if there's nowhere that we find a critical point? What might we expect about this graph?
Constantly decreasing.
Yeah, it's going to be either the whole thing is either increasing or the whole thing is decreasing. It's one of those two. So basically our number line is only going to have one sign on it. So let's think about it then. What do you think? Will the derivative always be positive or always be negative? Yeah, it's always going to be positive. This piece is positive, and because I'm squaring, I don't really need to check that one too hard. That'll be 2 positives. So this number line here is always positive. This function is always increasing. That's why we found no critical points. Okay. So this is where the algebra can be a little. I'm going to use another slide because I need a little bit more space. So the derivative was. I'm sorry, that was just e to the x. So I'm just transferring it over. Okay, so I'll walk you through the second derivative here. Second derivative, I'm going to move these back up to the top because product rule, I prefer the product rule. I think that's going to be easier to work with. So I'm going to do it like this. Okay, you sure you don't want to, this is the, if you're thinking a group hug is a good idea, this is the spot right here. No? Yes, sorry, there should be a negative there. Okay, so here we go. Second derivative, it's going to use the product rule. So the derivative for the first piece is going to be negative e to the negative x times the second. Now, the derivative of the second piece, that's going to mean I multiply by -2. And now it's to the -3. And I have to multiply it by the inside here, which is e to the negative x. So I get another one of these pieces from the chain rule. There we go. It's like a human computer. Is that good, eh? No? Okay. So now, we're going to need to do a little factoring here in order to make this something we can actually do algebra on. Because at its current state, it looks pretty challenging. So I'm going to factor out this a couple of things here. So first of all, let me show you both pieces have this. Okay, and both pieces also have. Let's go blue highlighter, I guess. Both pieces also have this. So I'm going to factor those pieces out. Okay, to help me solve the and find inflection points. So if I take them out, it'll be negative e to the negative x, 1 plus e to the negative x. And I can take out at least the -2. So let's see what I'm left with. Yeah, so the nice part, that one's nice. There's only one left there. What's left though here? Well, the pieces that are left over are these guys that I didn't highlight. So I guess I could call that subtract 2e to the x. Subtract 2. One more time. Subtract 2e to the negative x.
Isn't there still a 1 plus e negative x left though?
Yeah.
And a, thank you, 1 plus e to the negative x. Like that? Okay. Is that,
Yes.
okay, holy smokes. We're almost there. We're almost there. Okay. So, let's ask ourselves then, where can we make these things equal 0? We've already talked about this here. This is kind of like the first derivative up here. We've already talked about why this one can't equal to 0. So there's nowhere here that it would be equal to 0 or undefined. So we don't worry about that piece. The only piece we're looking at is, can we make this one possibly equal to 0? Okay, let's take a look here. It would be 1 minus 2 e to the x, 1 plus e to the negative x equals 0. Is this possible? So let's, oops, is there a mistake up there? One plus 2? I think it's negative because I factored out a negative e to the x. So only one negative sign? As I told you, it was going to be a good algebraic one, right? You didn't want to do that. I understand, you know, I understand you didn't want to do the group hug, but this one's, it's up there. It's a tough one. Okay. So, let's just put it this way. Being you guys are up there now. You're right at the top of your school in mathematics. You're really good at it, and you like being lazy at math. So if you had to be lazy, what's the first place you'd guess if you had to pick a value here?
0.
Good, because 0 makes all those e's disappear. So let's just try it and see what happens. So that'll be 1 minus, okay, 2 over 1. 1 minus 2 over 2. 1 minus 1. So yay, we found it. At x equals 0, there's one place that it works. So, for all our number line now, all we need is a 0 on there. So I'm going to go back to the other slide to put that on there. I'll just give you a minute in case you're still copying. Probably not, but next. Okay, so let's finish where we were at, which is second derivative. Okay. And we're going to plug the second derivative into the calculator, possibly to figure out where it's positive, where it's negative. All right, so I have, don't worry, I went and did it for you. I think, anyways, I'll have to double check. I'm not sure that I've got the correct answer here, but I can verify that once I look at the picture. So I get positive on this side and negative on this side. Okay. And as if you didn't think that that was bad enough, there's one other thing we haven't talked about in this. What haven't we mentioned? Asymptotes. We haven't talked about asymptotes. So let's go back to limits and figure out if there's any asymptotes here. 1 over 1 plus e to the negative x. So limit as x goes to infinity of 1 over 1 plus e to the negative x. So tell me what's going to happen here as I go to towards infinity. So like if I put e to the negative 10 in there, and then e to the negative 100, e to the negative 1,000, where is it going to go towards? 0, yes. This piece is going to slowly fade out because it's raising it to a negative exponent. So that means I'd have 1. Are there any other asymptotes? Some of you might be like, well, there must be, or you wouldn't ask us. Well, this is the right side of our graph. Let's check what happens as we go to the left side of the graph. All right, Ming, you want to tell us about this one?
0.
Well, tell me about this again is what I'm asking.
It goes to infinity.
Right, this piece is going to become infinite. So constant divided by infinity, this is going to go towards 0. So on the left side of my graph, I'm going to expect an asymptote of 0, while on the right side, I'm going to expect an asymptote of 1. Okay, so let me show you what that picture then would look like. Put it all together. Okay, so there's an asymptote at 0. There's an asymptote at 1. And the only point we had was at 0. So if I put in the point 0, I will also get out 1/2 as my value. So there's my point of reference. This graph is always increasing. It's always increasing. Concave up on this side. So it's going to look kind of like this. And then concave down on this side. They'll switch and go like this. There. I know you're thinking all of that just for this. I kind of feel the same way. But anyway, let's see here. I promise you I'll have lots of time for you to work on these. I think I am going to do that last question, which is way, way easier than what we just did. This was like if, I don't know, let's say if like Harvard and Yale and Princeton all decided to get together and make like the worst calculus exam for their undergrads, maybe it would have something like that on it. But anyways, anyone planning on going to Harvard, Yale, or Princeton?
I don't even know where any of those are.
Boston. Don't know where. I should probably know where Yale is. Anybody know where Yale is?
Mars.
Probably not Mars, but. Okay. Plot the. Let's plot this graph here to take a look at it. I'll bring up the graphs on the laptop for you. Okay, so I'm going to type them in here. So we got x squared minus 5x minus 1 and x minus 3. So here's the first graph. I'm going to make my range a little further out. So let's go maybe negative 15 to 15. And I'm going to put in also just a nice, do you remember the days when all you had to deal with was these nice simple lines? Remember those? Don't you miss those days? Well, here's what I want you to notice about this graph here. It has an asymptote in it. Do you see the asymptote? Yeah, it is the line. I mean, well, there's a reason I put them together. But do you actually see that it's hugging along the line? It's not crossing the line. It's doing what an asymptote normally does. Only this one's not vertical. It's not horizontal. This one's called a slant. Okay, so it's pretty... Yeah. I knew you'd be excited to hear that, but it's pretty easy to find a slant asymptote. That's what I'm going to show you how to do, and then we'll try doing a sketch with a slant asymptote. Okay? So, so for a minute, we get to go back to Math 10. That's good news, right? We're going to do some long division, and then that'll figure out what the slant asymptote is.
Two fun things involved.
So I'm going to do it this way. Hands up if you remember what I'm doing. Okay, so, no, I do not. You can do long division, or this is the synthetic division that was a shortcut you might have learned. So this is, I'm going to multiply these together, put the result there, add them up, multiply them together, add them up. So what this says is it's x minus 2, remainder negative 7. So here's how I could write that as a division statement. I could write x squared minus 5x minus 1 over x minus 3 is equal to x minus 2 plus negative 7 over, what was it, x minus 3? The remainder. Let me just... Okay, so... if they're equivalent, this is the one that tells us where the slant asymptotes, whoops, that's not a pen. This is the one that tells us where the slant asymptotes are, because as I go x towards infinity or negative infinity, this term becomes a 0, and all I'm left with is that line. So that's why as we get larger and larger, all I'm left with is the line. It's just that you wouldn't see it if it was written down in this fashion. You'd probably have to have it written down in the one over here with the long division statement. So I'll do the old-fashioned long division for you in the next one in case you don't remember the shortcut. But we're going to do the same thing. We're going to look for the slant asymptote here to help us graph this. So here's the way the old long division that is a little slower goes. So you have x squared minus 2x plus 4. So you're going to line up the first two terms, and that means I want to put an x to make x times x equal x squared. That leaves me with x squared minus 2x. So there's nothing left over. Bring down the 4. And now when I try to line them up, the only way to get a 0, well, you probably wouldn't do it, but you'd have a 0 times a 0. So that would leave me with nothing and remainder 4. So I could rewrite that as x squared minus 2x plus 4 divided by x minus 2 is, let's see here, x plus 4 over x minus 2. So again, as I go towards infinity, this piece would be gone. So here's my slant asymptote, and we'll put that on the graph. So y equals x is a pretty easy one to put into this picture. And so the graph's going to hug this line. And now we can do what we can with this curve. So let's find the first derivative and the second derivative. Okay, so let me just point out something to you here. You can go ahead and product rule this. You can go ahead and quotient rule it. But we did all that work to figure out how to separate it into two pieces. So why not build on that? If you were to use the work we've already done, which says here that, let me tidy this up a little bit. It says right here that they're the same thing. So you get to choose which derivative do you like better. I decided I liked the second one better. So in this case, if I want to find out where does this equal to 0, I can actually tell you without having to, I can actually figure that out without needing to do any complex solving. Can you see the answer? Any ideas? Four is one place, 0 is the other. But you could do it like this: 1 minus 4 over x minus 2 squared equals to 0. Then 1 equals 4. And we can keep solving it like this. So I'll square root this. That means x minus 2 is plus or minus 2. And x is plus or minus 2 plus 2 more. So 2 plus 2 is 4. 2 minus 2 is 0. Those are my two critical points. But again, I think some of you, like I said, can probably see it just by looking at the first one. So it's not a bad way to deal with it if you've used the same derivative or the same function I did for that derivative. Okay. Now again, you might have this complicated looking fraction from whatever, or the product rule. You get to look at mine. Would you rather do this for the second derivative or what you started with? Okay, hands up if you think this will make a nice second derivative. Yeah, okay, this is going to be a lot nicer than if you would have jumped right into quotient rule. So the point here again is it's not just useful for a slant asymptote. It can split this equation from a quotient rule into something nicer. So we could do it that way. So let's rewrite this. That first derivative would be like 1 minus 4 times x minus 2 to the negative 2. Oh, it's already up there. Very clever, Mr. Joyce. Very clever. It's already up here. Okay, so I'm going to use this one for my derivative because it's already ready for the product rule. So I'm going to have 8 times x minus 2 to the negative 3. So that's 8 over x minus 2 cubed. Okay, can we find any inflection points here? Any place that it might equal 0 or be undefined?
Undefined at 2.
So there's a problem at x equals 2. Did we forget anything in the first derivative? Yeah, it also has a problem up here. When x equals 2, it's undefined. So that means there's a critical point that we forgot. Okay, so we actually have those three and this single place for the second derivative. Okay, so now we can make up our number lines and start graphing. So first number line has 3 plots on it. One at 0, 2, and at 4. Then the second derivative only has a plot here at 2. Okay, so we'll use a calculator to help us. Probably been through enough torture for one day. Okay, so the pattern that I get is I get a positive, then I get negative, and then I get a negative, and then I get a positive.
That's not if it was 0, then it was
So for the last one, I have a negative here and a positive on this side. So now we can go and plot these points at 0, 4, and 2 and come up with our sketch. Okay, so at x equals 0, let's see here, I'm running out of, why don't we do it up here? At x equals 0, I'm going to end up with 4 over negative 2, so I'll be at negative 2. The other places were 4 and 2. So at x equals 2, what happens? Asymptote, right? So we'll put ASYM. So here we go. And at x equals 4, that means I have 16 minus 8. So that's 8, which would be a 12. So it'll be 12 over 6, which is 2. Sorry. That's 12 over 2, which is 6. Okay, so let's plot those points. 0 and down to negative 2. The other one, which is at 4 and positive 6. You probably can get an idea that the graph has to be doing something in here because it can't escape those asymptotes. So we just have to figure out about what that is. Okay. So if we look at the first piece, my number lines are too far away. We're increasing and concave down. So increasing and concave down is going to look like this. Then when we hit the second part, we are decreasing and concave down. So it's going to be like this. And in the last part, I am decreasing and concave up. So decreasing and concave up here, then increasing and concave up. Okay. So that's what this graph would look like if we were able to use a graphing calculator.